today we have two speakers. We have Yifan Zhong, who's currently a first-year PhD student in the Pair Lab at Peking University, guided by Professor Yaodong Yang. His research interests include reinforcement learning, multi-agent systems, and large language models. He's published several academic papers in top journals and conferences. Our second speaker is Jiarong Liu, who's currently a senior student at Beihang University, interning in the Pair Lab at Peking University under the guidance of Prof. Yaodong Yang. His research interests include reinforcement learning and multi-agent systems, and he's a co-first author of the paper that will be presented, which was presented at ICLEAR this year. The paper titles Maximum Entropy Heterogeneous-Agent Reinforcement Learning, but I think they've got a cool acronym for that. I think I will hand over to Yifan, so if you guys can share your screen, and then happy for you to go ahead.
Yeah, sure. Thank you. Sorry, 1 second. Wait. Here. Is that correct? Is the
yes.
front page? Okay. All right. All right. Thank you for hosting. Today, we are so excited to be here to present our work titled Maximum Entropy Heterogeneous-Agent Reinforcement Learning at your esteemed reading group. And this paper has been accepted to ICLEAR 2024 as a spotlight paper. And like last month, we just went to Vienna, Austria to present it at the poster session. And so we are very happy to give another talk on it. So let's begin. Today I will divide the talk into 3 parts. The first part, I will briefly introduce to you the background of cooperative multi-agent reinforcement learning, and then we will discuss how we approach this problem, how we resolve the challenges, and how we propose our methods. And finally, I will show some experimental results. So firstly, let's think about the cooperative games, which are the focus of our paper. So what are cooperative games? It's actually a kind of games in which participants cooperate to achieve common goals, as shown in the left picture. In this process, cooperation is a must. Acting individually can lead to suboptimal outcomes. And there are lots of examples around us. For example, like in the ocean, fish swim in schools for hunting, and also in the during hunting, these 2 different species also hunt together. And on the left, these are the same species, and on the right, these are different species, but they can all cooperate very well. And also in the robotic applications, there are also lots of examples. For example, the drone swarms will coordinate to complete some tasks. And on the right, heterogeneous robots will cooperate to do the assembly task. And there are also lots of multi-agent testing benchmarks in our research community. For example, the famous SMAC benchmark, the Google Research Football, and also the Bi-DexHands. These are also some of the benchmarks that we use to test our algorithms, and I will show in just a minute. So the significance of solving cooperative games is that it enables coordination among multiple intelligent agents, and it also proposes better solutions to large-scale control. It has lots of applications in robotics, military, medicine, engineering, finance, traffic, etc. Currently, the dominating learning framework to solve cooperative games is the cooperative multi-agent reinforcement learning with centralized training and decentralized execution. There are some types of algorithms, for example, value decomposition, decomposed actor-critic, and also multi-agent policy gradients. Although the current work, the work before our work, has achieved some good performance, but they suffer from some severe limitations. Here we focus on MAPPO and HAPPO. The former one directly extends PPO to multi-agent reinforcement learning, and the latter one, although it is guaranteed of monotonic improvement and Nash equilibrium convergence, it, along with MAPPO, suffer from the crucial challenge of converging to suboptimal Nash equilibrium, or like now finding the optimal joint solutions. And here we present a simple example to show this problem. So this is actually a single state problem, and there's only one state, and there are two agents. Each agent has three actions, A, B, and C, and the reward matrix is shown on the left. You see that the best policy is obviously CC, and here we try to consider the case where, like in neural network optimization, or like in deep learning training, like due to the initialization or initial training, the agents may be initialized to some policies that is quite far from the best policy. Here, they are quite close to the joint policy AA, which is, well, suboptimal. And we see that with HAPPO and MAPPO, they deterministically converge to the joint policy of AA, which is suboptimal. And in the paper, we present a numerical computation to show this. So why is this? Why cannot they learn the optimal policy CC? We find that the problem is actually with the standard joint objective they optimize, shown on the right. The joint objective is also actually only consists of the joint rewards, which discourages any unilateral deviation from the local optimum. And it's also only at another result that is proven by former researchers is that, like in these kind of problems, there always exists a deterministic solution, so that it does not encourages the exploration. And the final optimization result of these algorithms are all deterministic. So we think that the viable solution for this challenge is to learn stochastic policies. And now we discuss our methods. So our method is actually inspired by a prominent work done by Sergey Levin called Control as Inference. It embeds the reinforcement learning problem into a probabilistic graphical model and conduct variational inference on it to derive a maximum entropy objective. We also embed our multi-agent reinforcement learning problem into this probabilistic graphical model, where we have the state in each time step, and also the actions from all agents. The number of agents is n. And we also introduce a binary optimality variable called OT, which states that whether the current action in this state is optimal. And the probability of it being optimal is proportional to the exponential of the reward of the current state and actions. So by conducting, and our goal is to optimize the probability of O1 through T being all being optimal. And like inspired by the work by Levin, we conduct variational inference to this probability, and we derive a lower bound, which can be rearranged to the last line on this slide, which is the maximum entropy objective of multi-agent reinforcement learning. You see, compared to the former standard objective, we now have an entropy term, which encourages not only the policy to be stochastic, but to have high entropy, but it also encourages the policy to arrive at the states that will have a high entropy, so that it fulfills our goal for the stochastic policies. By including the entropy into our objective, we find that the solution concept is no longer Nash equilibrium. It now should be quantal response equilibrium, which is a generalization of Nash equilibrium. It does not assign probability solely to the highest payoff actions, but instead it assigns probability according to the payoffs of all actions. So that it's actually a stochastic policy instead of a deterministic one. And in our paper, we prove a theoretical result that when the policy converges to quantum response equilibrium, it's the form of the policy actually is shown as here, that it's actually an energy-based model and assigning probability according to the Q values of those actions. So which aligns with the former introduction to QRE. So we adopt this solution concept, and our goal is to learn the joint policy that will be a QRE in this maximum entropy multi-agent reinforcement learning problem. And before discussing our algorithm, we actually need another definition, which is the multi-agent soft Q functions. This is because in analyzing or numerically when we derive some properties of multi-agent reinforcement learning, we always need to consider a subset of the agents. So that here we define the Q value of a subset of agent actions as this equation. And it's actually a pretty general definition because when m goes to n, it represents the joint soft Q function. And when m is 0, it represents the value function. So now we discuss the main theorem, or the first part of our theorem. First part of our theoretical results, which is called the Heterogeneous-Agent Soft Policy Iteration, which is used to optimize the maximum entropy objective, and we also prove its theoretical properties. This policy iteration actually has two parts. The first part is quite standard. It's the policy evaluation part. It's actually just a direct application of the soft Bellman update. And we also show that if we iteratively apply the soft Bellman update, the Q function will actually converge to the ground truth Q function for the current policy. But actually, as we adopt the policy iteration approach, we do not run the policy evaluation to convergence, but instead we alternate between policy evaluation and policy improvement. The policy improvement part draws some inspiration from the prominent work Soft Actor-Critic, which says that the policy, it's a single agent work, and it says that the policy can be optimized by minimizing the KL divergence between the policy and the exponential of action values. So the joint policy also follows this optimization target, but what we want is actually how to optimize each target by themselves, because the joint optimization target is actually have quite high computational complexity, so that we actually want to decompose it into agent-wise optimization target. And this to do this, we actually is based on the advantage decomposition result, which is proposed in Heterogeneous-Agent Reinforcement Learning paper. And with that theoretical result, we further decompose this joint objective into the objective of each agent, and this objective actually minimizes the KL divergence of its policy with the exponential of multi-agent Q functions. And with this optimization target, we actually prove that they can be combined to when they all have finished their optimization process, the derived new policy actually have a better maximum entropy objective value than the older one, so that it achieves the monotonic improvement property. And combined with policy evaluation step, we show that actually this policy iteration process allows the policy sequence to finally converge to a QRE policy, which is what we want. So we show that this policy iteration process is actually can actually pretty good like solve the task pretty well. And
is it fine to ask a quick question?
Yeah, sure.
So okay, I guess I understand your approach, but I'm still trying to understand, why do we want to do the joint policy decomposition? Are you saying it's easier or more tractable to learn the individual policies? Is that the main reason, or?
Yes, because like when we have lots of agents, the complexity of doing like joint policy optimization can be pretty high. Yeah, so that's I think that's the main reason. So we if we can decompose it into like agent-wise target, then it can be better optimized. And another reason I think is like application, as we want decentralized execution, we actually parameterize every agent's policy with a separate network, so that optimizing like the networks separately can be easier than like optimizing them together.
Okay, cool. I think it makes sense. I'm just trying to think from like so the joint policy represents some centralized policy, and you're decomposing the centralized joint policy into agent level policies.
I think not quite, because as I just mentioned, we want a decentralized execution, so we actually only have agent level policies. In practice, we only have agent level networks. We do not have a joint network. So actually, the joint policy is only used for theoretical derivations. It's actually considered as the multiplication of all agents' probabilities, but we do not have an explicit network to represent it.
Okay, cool. Yeah, that's cool. Makes sense. Thanks.
Yeah, sure, no problem. So I will continue. So just now I introduced the theory, which is the policy iteration theory. But in practice, we need to like parameterize those network with neural networks. So we parameterize it with like Q theta and pi phi, and we learn them with back propagation. So the critic is learned with the standard TD learning paradigm, and the actors can be learned by expanding the KL divergence term, and we find that it can be written as this equation, and this can be optimized pretty efficiently with modern autograd systems. And finally, we also want to generalize the theory to cover more algorithms and to gain like deeper theoretical understandings. So to this end, we actually introduce two new necessary operators in order to provide a range of solutions to the maximum entropy MARL problems. They are the drift functionals and the neighborhood operators. These have been proposed in former work, such as heterogeneous agent reinforcement learning, because these are used to establish a general framework for the MARL problem. And the main function of these operators are that the drift functional will serve as some soft constraints, and such as the KL divergence is more like a penalty, and the neighborhood operator will serve as a hard constraints, a constraint for the optimization problem. So with this operators defined, we actually arrive at the the final theoretical framework called the maximum entropy heterogeneous agent mirror learning. It involves two steps. The first step is the policy evaluation step, which is still very standard. And the second step is the generalized heterogeneous agent soft policy improvement step, which augments the objective just now with the neighborhood constraints and the drift functional. So we see that it can actually, these operators can be can be materialized into lots of constraints such as KL divergence or KL neighborhoods or like similar ones to impose some constraints on the policy improvements so that to make it have some other desirable properties. And in our paper, we also prove that with this generalized framework, the algorithms derived from this framework all are guaranteed of the monotonic improvement of maximum entropy objective and also the QRE convergence. And so finally, I will discuss the experiments that we have conducted.
We actually ask a quick question before we move on to the experiments.
Yeah, sure.
Okay, I think maybe a lot of people are not very familiar with, I guess, sequential multi-agent RL. Do you mind maybe just talking through that, speaking about, I think there's like sequential policy updates. And
yeah, sure. So actually, let's, I think, so I do not have a slide, a page in this slide, but I can like just discuss this paradigm.
Sure.
Actually, at the beginning of multi-agent reinforcement learning research, lots of the algorithms are derived by just simply extending the single agent algorithms into the multi-agent scenarios, and they mostly optimize all agents simultaneously, like when they collect some data and they update all the agents at once, like at the same time. However, this is quite unstable because each agent is unaware of the optimization direction of other agents, so that their optimization directions may conflict. And so one solution to this problem, actually very intuitive one, is to optimize them sequentially. So this sequential update paradigm is formalized in the HAPPO paper because they derive a multi-agent advantage decomposition lemma, which shows that which is a general equality, showing that the joint advantage function can be decomposed into individual advantage functions, and it's substantiates the sequential update paradigm, and lots of algorithms have been proposed thereafter to following this paradigm, and they have been shown to work pretty well. Yeah.
Yeah, cool. Thanks. Yeah, no, that's a great explanation. Just to clarify.
Yeah, sure, no problem. So finally, I'll discuss the experiments. Actually, we conducted the experiments on both the matrix game as a illustration, and also 6 common benchmarks, including multi-agent particle environments, multi-agent MuJoCo, SMAC, Google Research Football, Bi-DexHands, and aircraft games. To handle the discrete action space in these benchmarks, we also implement Gumball softmax to make our algorithm work on them. So here are the main results. The main results include we achieve Pareto optimality in matrix game if the temperature is appropriate. And we also achieve best performance in 31 out of 35 tasks compared to previous SOTA methods. We also achieve higher training speed, higher training stability, and higher learning speed. We also benefit from improved exploration. So here is the result on the matrix game. On the matrix game, we show that we first show a numerical computation of the of our algorithm's learning process. We show that for different alpha, which is the temperature, the probability after the first update and at convergence, we see that as alpha goes up, actually our algorithm allows the agents to escape from the local optimum and converge to some global optimum points. So it shows that the stochasticity is pretty powerful. And we also show this in empirical validations that with different alpha, our algorithm can actually converge to better solutions. And here we show the experiments results on the Bi-DexHands benchmark. On this benchmark, you see the dark purple line is HASAC. It actually achieves like high reward in very short time, and it converges pretty fast. And here is the result on multi-agent MuJoCo. And here we see that HASAC also achieves pretty good performance. And here is the results on the SMAC, which is a very standard benchmark. On this benchmark, HASAC mostly achieves pretty high performance compared to strong baselines. And here's the learning curve. And here we show some extra experiments on this benchmarks, and we show that HASAC also mostly achieves pretty good performance, like compared to other previous methods. And finally, we did some ablation study. This ablation study, we investigate stochasticity and the impact of alpha. On the left, we show that with a stochastic policy, our algorithm can actually learn much better than the deterministic one. And secondly, with different alpha, our algorithm can actually achieve like different return, and this, in some cases, this can be tuned, but we also implement another method, another improvement trick that can tune the alpha automatically. So it's also quite beneficial. So here are some related information to this work. The implementation is open sourced at this link. This repo has currently earned like nearly 400 stars, so please take a look. And also this is our paper, and this is the website of this work. And thank you all very much for listening. And I'm happy to take some questions. We'll all take the questions.
Cool, thanks so much for the excellent presentation. I have a few questions, but I will quickly ask if anyone else has any other questions. So maybe we can. Okay, Lucas.
Yeah.
Sorry.
Hi. Yeah.
We have a question.
Thank you very much for the talk. I hope you can hear me.
Yeah. Yes. Okay.
So yeah, I was curious about the Gumbel softmax part. You mentioned in the end that, of course, SAC kind of by nature is designed for continuous control tasks, and you use the Gumbel softmax to apply to discrete action space scenarios, and we've seen this in MATDBG, for example, as well, has done exactly the same. But at least I remember we noticed that a lot of experiments with the Gumbel softmax in MATDBG in particular seem to cause stability issues during training. And we assume this might be partly down to the fact that the Gumbel softmax is a biased estimator. Do you see any issues like that occurring when you use the Gumbel softmax? Do you see that in the discrete action space scenarios, your approach is slightly more unstable during training, or do you think kind of those issues do not really occur in your setting? And maybe do you have some ideas of why that might be the case?
Yes, in some cases, the HASAC cannot perfectly solve the task. For example, in some Google Research Football tasks, HASAC will perform unstable. So we didn't do lots of experiments on the Google Research Football. We think it might be due to the Gumbel softmax, and but HASAC also works very well on the SMAC. So I think a Gumbel Soft Actor-Critic might have some influence on some tasks, but we think that almost tasks it still works well. Yeah.
I see. Yeah. I mean, I suppose one key difference there by DDPG is also just the entire sequential update of policies, which seems to improve stability of training notably. So I suppose by kind of having that rather than the kind of synchronous updates of all agents at the same time in embedded DPG might also help to not have as much instability. But yeah, thank you.
Yeah, thank you.
Cool. I think we have another question from Atish.
Hi. So I see that there are a bunch of things introduced in this paper. One was sequential update, mirror learning, also maximum entropy. I don't think I found that in paper, but which of these things do you think have had the highest impact in getting good results? Maybe with an ablation.
I think the maximum entropy contributes to our algorithm's results the most. Because of the entropy term encourages the exploration, and which help our algorithms can usually converge to a higher reward equilibrium compared to the existing algorithms. And the mirror learning part, and since HASC didn't use the drift functional and neighborhood, the neighborhood for HAC is the whole policy space, and the drift functional is just 0. And we think the drift functional and the neighborhood operators are something that can be future researched. Yeah.
I see. Thanks. And maybe this might be a trivial thing, but how would is the heterogeneity an assumption in these algorithms? How would these algorithms work when there is no heterogeneity among agents?
Sorry?
Sorry.
Is heterogeneity assumed among the agents for these algorithms? How would
Yes,
these
yes.
algorithms perform when the agents are similar?
When the agents are similar, right?
It's a
When
simpler
the agents,
case. It's a simpler case of heterogeneous agent, right?
yes, when
Yes.
the agents are similar, we can still train the algorithm in a heterogeneous way, and it might take a longer time for training, but finally they can still learn the similar behaviors. I mean, the homogeneous settings can be viewed as a special case of heterogeneous agent setting.
Yeah, like our algorithm can be directly applied to the homogeneous settings because it's just a simpler case of the heterogeneous one. Our algorithm is actually designed for the general heterogeneous case. And what Jiarong just said about the slower training is actually compared with the parameter sharing.
Yes.
The parameter sharing paradigm, which may be beneficial in the homogeneous part, in the homogeneous settings. Yeah, but in general, our algorithm will definitely be more general and more applicable.
I see. Thanks.
Yeah, no problem.
Cool. I guess while we maybe wait for some hands, I'll also ask a couple of questions. My first question was on sort of the matrix game results. I was like, do you have any intuition as to why MAPPO couldn't solve this? Because usually there's some entropy bonus applied to PPO to like encourage the policies to be stochastic. Do you have any intuition as to why, let's say, the MaxEnt formulation allowed this to be learned while the like entropy bonus like tricks didn't work?
Yes. In practice, PPO will use entropy regularization. But in this matrix game, we didn't implement PPO with entropy regularization because in this single state problem, if PPO uses the entropy regularization, then it is actually maximize the maximum entropy objective. Compared to the standard objective, maximum entropy objective not only maximize the policy's entropy, and it will encourage the agents to arrive at the states where the state is has higher entropy. So in the experimental section, we can see that when PPO uses the entropy regularization, HASAC still can achieve higher performance.
Okay, is this in the
Yeah.
other environments outside of the matrix games?
Yes, outside the matrix game, PPO uses entropy regularization, but in the matrix game, PPO does not.
Okay, cool. Then my next question is related to alpha. I think maybe in the appendix there was some more information. But is alpha, is it always kept constant? Is it ever decayed? Did you guys experiment
Yes,
with
it
ideas
depends
related
on
to
the
that?
Okay, it depends on the tasks. Actually, HACC is quite sensitive to the alpha. So, and if we set the fixed alpha, and we need to tune it across different tasks, and as shown in the matrix game, when we set different alpha, the algorithm will converge to different quantal response equilibrium. And so, in order to alleviate the effect of alpha, we also implement the mechanism which can automatically tune the alpha, and it works well in most tasks.
Okay, cool. And that's in the appendix. I think you had like auto alpha or something
Yes.
that you mentioned.
Yes, we introduce auto alpha in appendix.
Okay, cool. Great. Do we have any other questions from any of the attendees? Just double check through my questions. Okay, we have a question from Elliot. Go ahead.
Okay.
Hey, sorry, my connection is quite bad, so hopefully the question gets across. I wonder if you could explain a bit about the relationship between this kind of MaxEnt RL and entropy regularization in, for example, MAPO. So I guess it's quite normal to augment the reward function in MAPO, or the policy objective in MAPO, with a term which maximizes entropy. And the objective function looks quite similar to what you have from the practical implementation thing that the loss function that you showed in your presentation. So yeah, I wonder if you could explain a bit, maybe what the relationship between the two are, like how are they different, and maybe how are they similar?
I think this is similar to the question just now, right? Like the entropy regularization and the maximum entropy paradigm.
Oh, sorry, did somebody just ask this? Sorry, my connection is really bad, so I'm struggling to even hear what people are saying. But was this just asked?
Yeah, it's okay, it's okay. Jiarong, will you repeat your answer?
You mean the difference and relationship between the entropy regularization and the maximum entropy objective, right?
Yeah.
Yeah. The entropy regularization used in PPO, it's only used in the policy update step, and it encourages the policies to maximize its policies entropy, and just it. But maximum entropy objective not only maximizes the policies entropy, but it encourages the policies to arrive at a state with higher entropy, because the entropy is added into the final objective, and PPO with entropy regularization is still maximizes the standard objective. So it does not encourage the policies to arrive at the state with higher entropy. So the stochasticity of HASAC will be better than the entropy regularization method.
I see. So if we added the entropy term into the critic, so now this is taking into account the bootstrapping and all of this kind of thing, then do you think this would be a maximum entropy approach, or there's still something missing?
You mean adding the entropy into the PPO update step?
Into the like the update for the value network in PPO. You think this would
Yes.
like address what you just said, or there's still something?
Yes, I think if we want to use PPO to maximize the maximum entropy objective, I think the critic we should also add the entropy term into the critic.
Okay.
Not only the policy update step. Right.
Okay, I see. Thank you. Apologies if that was already asked. I as I say, my connection is pretty bad. I just connected a few minutes ago, so but thank you.
Okay, thank you.
Okay, cool, thanks. Do we have any other questions? I see some hands are up, but I think they may be just hands that were left up. Okay, cool. I don't think we have any questions. Then yeah, if that's it, thanks so much for the great presentation. And yeah, thanks for talking to us about your work, and thanks for making time. And have a good day, everyone, and see you at the next reading group meeting. Bye.
Yeah, thank you.
Thank you.